You're going to be taking the results from this video to plot a VI graph for a silicon diode. Your results should look something like this when graphically plotted. In reverse bias, unless we use very large voltages, which won't be safe to use today, then only very small currents will flow. In forward bias, then after you reach a voltage round about 0.7 volts for a silicon diode, then the current starts to increase quite quickly. So that's what we're looking for. Let's see if we get it from the results. Now, the diode that I'm going to be using, this general purpose diode, there's a little information here in the data sheet that might help you. You can see that the reverse voltage, when it starts to break down, is 35 volts RMS or 50 volts peak voltage, and so I won't be using that. But the reverse current that we're looking at there is only about 5 microamps. So again, we should be able to detect that, but it's only using a microammeter. And then in the forward voltage on the graph on the left, you'll see that depending on the temperature, around 0.6, 0.7, 0.8 volts will be required. But you can also see, remember this is a log graph paper that they're using here, that as the voltage goes above that, the current increases very quickly up towards 1 amp. And again, in the interest of safety, we need to make sure that the voltages aren't too great. In your report, I'm going to want you to draw a circuit diagram. You'll need to use standard circuit symbols, including the circuit for a variable DC supply and for a conventional silicon diode. We'll also have a resistor in the circuit, and the resistor that we're going to be using is of 100 ohms. And so you can see there that the stripes in fact will be brown, black, 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 although hard to see on the picture there. But this is the circuit, there is the diode, and the diode is going to be connected to a digital multimeter being used as a voltmeter. There is the variable DC supply connected in a circuit with the diode in series with the resistor there, the 100 ohm resistor. And then you can also see connected to it is the ammeter, which we've got connected absolutely into the circuit in series. The digital multimeter that we're using as a voltmeter will be added in parallel later. Now, if you can see the DC supply, that it's actually got 2 dials there for the voltage. One is the coarse setting, and then the second on the left is the fine setting, and we will need to use a combination of the two, and it's still quite tricky to get the readings to stabilize at the exact voltage levels that you're looking for in order to plot a graph. So you'll have to bear with us and make sure that we adjust those gradually until we get the right results. Now, before we carry on with the experiment, I'm going to use the multimeter on its ohm setting. First, we put a resistor in the circuit simply to make sure that when the diode starts to conduct, that the current doesn't increase so high to cause any kind of damage to the components. As you can see, it is 99.5 ohms, roughly 100 ohms, but you don't actually need that for any of the graphs or calculation. It's just there as a protective resistor. Let's have a look at the resistance of the diode itself. And in forward bias, it has got a small resistance at the small current that's going through it from the multimeter, but it will conduct current in that direction. If we put it in reverse bias, then the small current coming from the digital multimeter cannot go through. It says OL for open loop, effectively a very large resistance. Now, there's one last setting you can use, which is the diode setting on the multimeter. Make sure you've got your pen and paper ready to start taking results now. But I'm going to put the ammeter on to the milliamp setting and make sure that that's connected correctly to there. But on the digital multimeter, before I proceed further, let me put it on that diode symbol. And what that does is send a small current through the diode, and it gives an approximate measurement. You can see 0.87 volts, about 0.6 volts before it will start to take any significant forward current. Let's now start taking the readings in forward bias. So let's complete the circuits and start to increase the voltage, to start with 100 millivolts, or as close as we can to get it. As you can see on the left, the voltmeter reading is being adjusted. On the right, on the current, you will see that there is 0 showing. There is 0 milliamps. At this low level of voltage, we're not going to get any current. Let's increase that a little bit, and let's try and read, let's say 0.3 of a volt, 300 millivolts. But you can still see at this stage, whatever readings we take from the voltmeter, that we have got 0 milliamps. So that's pretty close there to 0.3 volts, but still 0 milliamps. Again, make sure that you're taking whatever results you think are appropriate as the meters change. Okay, let's have a look at 0.4 volts, and you can see for the first time we begin to get a very slight reading. That is only 0.01 of a milliamp. But as we now start to move up, let's see, as we get to 0.5 volts, you can see that we begin to get a little bit more current that can be measured. We're now at about 0.11 milliamps, possibly 0.12. You take the reading that you think is correct for 0.5 volts. Now just adjusting for 0.60 volts. You can see that we have now gone over 1 milliamp. And as I start to increase, now up to 0.7 volts, the milliamps are starting to increase again. I will therefore look for 0.65 volts as the current has been increasing by such a large amount at this stage, or relatively speaking. From 0.65, let's go up to 0.70. Again, the fine control is quite tricky to get precise. And you can see we're nearly now at 10 milliamps, not quite. So again, let's start to increase. Looking at the increase I'm getting there on the ammeter, let's just take the next reading at 0.72 volts, 0.720 hopefully. A reading for 0.730 volts. .740 volts. and I'll leave it for you to follow as we go up through the scales to decide which points you want to take measurements from as I adjust. We're now up, as you can see, 0.780 volts, and the reading on the digital supply itself behind, as you can see, is actually over 8 volts, now coming up towards 10 volts. So remember that most of that power supply's voltage is now being taken by the resistor rather than the diode, which is increasingly becoming a very good conductor. So a large voltage is beginning to take place across that resistor. So we need to be careful not to go too far now with our measurements. Again, we're now up over 100 milliamps, so I'm just going to take a couple more readings before the voltages and currents start to get too high, as that diode becomes effectively a very good conductor. This is the reason why at this stage the point of the resistor is to make sure that the current doesn't increase so large as to cause damage to the various meters and other components. The resistor itself, of course, can easily be replaced if necessary. We've now got 0.8 volts across the diode, over 15 volts from the power supply itself. And one thing that I can't record for you is that at this point you're beginning to get the smell of rather hot components. So time to turn things off and say that that is the end of our recordings for forward bias. So now let's go on to reverse bias. Now the first thing we're going to need to do is to adjust the wiring on the breadboard slightly so that now the current is coming through the ammeter, through the resistor, and then backwards, if you like, through the diode in reverse bias and then back to the digital power supply. So we've changed the polarity. Again, we'll be on the voltage setting. And let's first of all put the ammeter, once we've got the voltmeter connected in parallel, put the ammeter onto a milliamp setting and turn the power supply on, just to make sure what is happening as we increase the voltage. And you can see 5 volts, 6 volts, right up to 10 volts, and still 0.00 milliamps. So, as our data sheet showed us at the beginning, in fact for this we need to be on the micro ammeter scale in order to get any readings in reverse bias at all. So again, I'll leave you to take the measurements as I go up in 1 volt steps hopefully, and you can record the micro amps that are recorded on the digital multimeter. Now there may be a bit of a pattern developing with the results, but you'll be able to show that on your graph. Obviously with very different scales required for the reverse bias recordings as there will be for forward bias. I could keep going volt by volt, but there really isn't a great deal to be gained by doing so. I do not intend to go as far as the approximately 35 volts which was suggested on the data sheet would be the breakdown voltage for this particular diode. If we repeat the experiment with a special Zener diode, however, then it is worth proceeding to see what that breakdown voltage will be. But otherwise, I'll stop here with our final recording being at 10 volts. Okay, so last but not least, I need your report. It needs to include a circuit diagram, clear results tables with units, and above all, clear voltage current graphs for both forward and reverse bias.